Hi guys, today we're going to be talking about how to graph sine and cosine. So before we get started, I want you guys to not only have your notes out, but also have your unit circle out because we are going to be finding sine of a couple different values on our unit circle. One thing to also keep in mind that we have discovered in class is that the x and y coordinate points that we found around the unit circle are all of the cosine and sine values for those degrees or those radians. So something just to keep in mind while we are trying to figure out the values for sine in our unit circle over the interval 0 to 2 pi. So to get started, we want to put our labels for our scaling onto our graph. Because we're going from 0 to 2 pi, we will start at the origin 0, 0, and we will go all the way to the end at 2 pi. We know right in between 0 and 2 pi is going to be a single pi, and then just to get a couple more points, we know in between 0 and pi, we will have a pi over 2, and between pi and 2 pi, we will have a 3 pi over 2. We can also look at our unit circle. Since sine represents all of the y values of our coordinate points, we can look at the highest and lowest y values, and that will be a positive 1 and a negative 1. So we know this sine graph will go up to positive 1 and down to negative 1. So, in order to figure out how we can begin plotting points, let's look at our equation up above, y equals sine of x, and let's plug in our values, 0, pi over 2, pi, 3 pi over 2, and 2 pi, to figure out what sine at those values would equal. So, first, let's find sine of 0. We can use our unit circle, look at 0 radians, look at the coordinate point that corresponds with that, and see that at sine of 0, we would get a 0 value. So we can go ahead and plot the coordinate point 0, 0. Next, let's evaluate sine at 2 pi, pi over 2. So sine at pi over 2, we can find pi over 2 on our unit circle, which is equivalent to 90 degrees. The y value of that coordinate point is 1, so sine of pi over 2 is equal to 1. So we can go ahead and plot the coordinate point at pi over 2, 1. We can then evaluate sine of pi. We can locate pi on our unit circle, look at the y coordinate point, which is 0, so sine of pi is equal to 0. So we can plot the point pi 0. Sine of 3 pi over 2, we can go ahead and locate that on our unit circle, which is equivalent to 270 degrees. The y coordinate point is negative 1, so sine of 3 pi over 2 is equal to negative 1. So we can plot the point 3 pi over 2, negative 1. And then finally we can evaluate sine at 2 pi, which once again, like 0, is going to be equal to 0. So we have these nice coordinate points that we can now sketch a line through. This is going to create a very nice curve coming through all the points that starts going up, heads down, and then back to the center. A couple things to note on this graph, some new vocabulary terms for this chapter. We have the height of a wave, and this is called the amplitude. And then we have the length of a wave, and this is called the period. So if we were to extend our graph, we would continue seeing this waving motion, and our period is how long one wave is. And with the sine curve, we see that it starts at 0, heads up to 1, turns, comes down to -1, and then back up to 0. That'll be one wave for the sine curve. So now that we have our sine curve graph, let's go ahead and graph the cosine curve. Once again, we want to do this over the interval 0 to 2 pi. So we can scale our graph exactly how we scaled it for our sine curve. So we can start up at 0. In the middle of 0 and 2 pi is going to be pi. Halfway in between that will be pi over 2. And halfway between pi and 2 pi is going to be 3 pi over 2. All right. Once again, cosine is going to be all of the x values for the coordinate points around the unit circle. So if we look at the largest and smallest x value, we see that it goes all the way up to +1 and down to -1. So we can scale our y-axes as well. Now, exactly like we did with the sine graph, we can use our equation to evaluate cosine at our given scaling values. So first we'll evaluate cosine at 0. So cosine of 0, if we look at the x coordinate point on our unit circle, that is going to equal 1. So cosine is actually going to start up at 0, 1. If we take cosine of pi over 2, which once again is cosine of 90 degrees, we see that that x value of the coordinate point is 0. So at pi over 2, cosine equals 0. And we can evaluate cosine at pi, which looking at our unit circle, that x coordinate point is going to be -1. So cosine of pi is equal to -1. Cosine of 3 pi over 2 is equal to 0 according to our unit circle. And then finally, cosine of 2 pi, similar to 0, is equal to 1 again. So we can now sketch out our lines for this curve, which in this case, we started up at +1, passed through 0, went down to -1, came back up through 0, and passed through +1 again. So we can kind of see this looks very similar to the sine curve. We're just seeing a different part of the wave. But once again, the height of the wave is called the amplitude, and the length of the wave is called the period. So now knowing that, let's put some values to this. We have our two equations, y equals a sine b of x, and y equals a times cosine bx. Our a value represents our amplitude. And just like in previous chapters with function transformations, our a value is that vertical stretch. So this affects the height of the graph, since that represents our vertical stretch. The period is represented by our b value. So it's our b times our x within that function, within the trig function. And this is going to affect the length of the graph. So the amplitude affects the height, and the period affects the length of one wave. So we do have a formula for how long a period or how long one wave is going to be, depending on our transformations. So this period formula, if we're working in radians, is going to be 2 pi divided by b, or if we're working in degrees, will be 360 divided by b. A couple things to note. If we do not have a b value, if we are just looking at a normal sine or normal cosine curve, one period is going to be the length of 2 pi or 360 degrees because it is one cycle around the unit circle. However, this b value can change So for example, if I have a B value of 2, I'm going to see 2 waves within 360 degrees or within 2 pi. Or if my B value is a half, I'm only going to see half of that wave happen in 2 pi or 360 degrees. Something to note, if we have a negative in front of either the sine or the cosine curve, just like normal transformations, our entire graph is going to be reflected over the x-axis. For our first main example, we want to graph the function y equals 2 times the sine of x, and we're going to do this over the interval 0 to 360 degrees. So similarly to how we labeled our radians, we're first going to start at the origin, 0, and we will end at 360 degrees. So we can put our main quarters in between these. So in between 360 degrees and 0 is going to be 180 degrees. We will have 90 degrees in between that, and 270 degrees in between 180 and 360. And let me fix my markings, they're just a little off here. All right. Dependent on our function, we want to determine the a value and the b value so that we can use our period formula to figure out how long one period is going to equal. So our a value is going to be in front of the sine function, which is 2. So this means our amplitude, instead of going up to 1 like normal, is going to go all the way up to 2. And same thing, instead of going down to -1, like the usual function, this guy is going to go down to -2. Our b value is the term right in front of the x. And if we don't have the term, it's that invisible 1. So if we use our period formula in degrees, we have 360 degrees divided by our b value. So 360 degrees divided by 1 is going to be 360 degrees. So this means that we should see one wave in 360 degrees. So we can go ahead and start looking at how we can plot this. Our sine function, we know, started at 0, 0. So this guy, that starting value will not be affected by our transformations. Our next value, when we hit that pi over 2 or 90 degrees in degree values, we went up to 1. However, since our amplitude is 2, at 90 degrees we are going to go all the way up to 2. And then our pattern says go back to 0 for sine at 180 degrees. For 270 we're going to drop down because our amplitude is 2. We're going to drop all the way down to -2. And we come back up to 0 at 360 degrees. So we now have this nice sine curve. The difference between this one and the original one we drew up above, we come through all of our major points, which we've kind of quartered off our graph. And the main change is that we have a higher amplitude. So we see that our graph goes a lot higher than in our first example. Now on the back of your paper, let's go ahead and figure out the graph for y equals 2 sine of x over 4. And we are going to do this over degrees. So I'm going to change what I have written here. But our interval might be slightly different because we have a different b value. So let's first identify our a and b value. Our a value is going to be 2, so we know our amplitude is going to be 2. Our b value in this case is actually going to be 1/4. So we have 1/4 times x over here. So this means within 360 degrees, I should see 1/4 of the period. So now we can use our period formula to figure out how long one wavelength is actually going to be. So we're going to take 360 degrees and divide it by a fourth. When we are dividing fractions, we just have to multiply by the reciprocal. So we really have 360 times 4, which is going to equal 1,440. So this is going to be the distance for one wavelength. So we're actually going to change the interval to be 0 degrees is less than or equal to x, which is less than or equal to 1,440 degrees, just so we can make sure we see the full cycle. So labeling, we're going to start at 0. We're going to go all the way to 1,440 degrees, and we're going to use our normal pattern of quartering our graph off. So halfway between 0 and 1,140 is going to be 720 degrees. Halfway between 0 and 720 is 360. And then halfway between 720 and 1,440 is going to be 1,080. And once again, our amplitude goes all the way up to 2, since our A value is 2. So our graph is going to go from -2 to +2. And we are graphing the sine curve. So we know we start at 0. We're going to go all the way up to 2 at 360 degrees. We're going to go back down to 0 at 720 degrees. Down to -2 at 1,080 degrees, and then back up to 0 at 1,440 degrees. And then we can draw our nice sine curve. If we continued our graph, once again, our curve would just continue this same wave pattern. And one thing to note, we mentioned before that we should see a fourth of the period in 360 degrees. And as you can see by the highlighted portion, this is a fourth of our wave that you can see within 360 degrees. So that is what our B value is going to tell us. It's how many waves we can see in 360 degrees. All right, our next graph is going to be y equals cosine 2x. So first things first, we're going to identify our A value and our B value. Our A value, since we do not have a term in front of cosine, it is that invisible 1. And our B value is going to be 2, since that is the term in front of x. So what this means is that we should see 2 periods in 360 degrees. We will use our formula for the period to see how long one period is going to be. So we will take our 360 degrees, divide this by 2, since that is our B value, and this will give us 180 degrees. So that means one wave of our cosine graph will take 180 degrees. With this one, we'll graph this over the interval 0 to 360 degrees, just so we can see both of those wavelengths and kind of determine how that looks. So we'll mark our graph 0 to 360 degrees. Normally, we would have our 180 degrees, our 90 degrees, and our 270 degrees. However, since one wavelength is going to take us to 180 degrees, we want to make sure on the left side and the right side of this orange dashed line that I kind of plotted out that we have quartered that section as well. So in between 0 and 90 degrees, we're going to see 45 degrees. In between 90 and 180, we're going to see 135. In between 180 and 270, we'll have 225. And then in between 270 and 360, we will have 313 degrees. All right, our amplitude is just 1. So in this case, we only need to go up to +1 and down to -1. It is important to note that we are graphing our cosine curve, and our cosine curve starts up at the amplitude at 0. So our first coordinate point is going to be 0, 1. Then our cosine curve at the next quarter comes down to 0, moves to -1, moves back to 0, and then back up to our +1. So that is going to be one curve, one of the waves, not 180 degrees. But because we're graphing all the way out to 360, we can go ahead and continue our pattern. So we're going to be down again at 0, moving to -1, back to 0, and then all the way back up to that +1. So with our line, we're starting up, going down, coming back up, and then just continuing that same motion. So we can see that two periods, two of our wavelengths of cosine happen within 360 degrees, which represents the B value, and using our period formula, one of those waves then happened in 180 degrees. All right, now we will graph 1/3 cosine pi of x, and in this case, our A value is going to be 1/3, which means our amplitude is only going to go up to 1/3, as well as down to -1/3. And our B value in this case is pi, which means we should see pi part of the period in 360 degrees. However, because we're dealing with pi, it would be easier to deal in radians instead of degrees. So for this problem, we were going to change up the interval just a little bit. Using the period formula, we will take 2 pi divided by our B value, which is pi. Because we have a pi in the numerator and the denominator, we can cancel those out due to our rules of multiplication and division. And so our period is going to be a length of 2. So for this example, we will graph this over the interval 0 to 2. So we can change that on your worksheet. So this means for our markings, we'll start at the origin, come all the way to 2, and then we can quarter off our graph. So we will have our half, 1, and 3/2, and 2. Once again, our amplitude only goes up to 1/3. So we can mark this at 1/3, -1/3. If you want to change your spacing, that is totally fine. And then we are graphing the cosine, so this means we start up at our amplitude first. So we're going to start up at this 1/3, and our pattern is to head down to 0, down to our bottom, back to 0, and then back up to the top amplitude. And then we can sketch our curve in. So we can see our amplitude greatly affects the height of our wave. And then we're ending at 2 instead of 2 pi like normal, since our B value is pi. Finally, we want to be able to find the equation given the graph. So a couple things for the equation. First, we need to determine if it's going to be a sine or a cosine function. Because this starts at 0, 0, that tells me it's going to be a sine function right away. So I'm going to have y equals some sort of an A value, sine, some sort of a B value, and x. In order to determine the A value, all I need to do is look at the height of my wave, which is going to be 4. So my A value is going to be equivalent to 4. To determine the B value, we need to use the formula to help us solve. So that formula for the period was 2 pi divided by B, and that equaled 1 period's distance. So if I look at my curve, 1 period starts at 0 and ends at 6 pi. So that's going to be 1 period of my graph. So in my formula, I have 2 pi divided by my B value, which I don't know yet, but I do know that 1 period was the distance of 6 pi. So in order to solve this, I'm going to put 6 pi over 1 and cross multiply. So 2 pi times 1 gives me 2 pi. B times 6 pi gives me 6 pi times b. And then to get the b all by itself, I need to divide both sides by 6 pi. So we have 2 pi divided by 6 pi equals our b value, since these terms cancel out. We can see our pi terms cancel out, and then we can reduce the 2/6 to become 1/3. So our b value is going to be 1/3. We can also see this if we break up this 6 pi into thirds. We have our 2 pi, roughly our 4 pi, and we can see that about 1/3 of our sine curve is in that 2 pi. So here's our equation representing this graph. In our final example, once again we want to determine if we are using a sine or cosine function for this guy. Because it starts at 0, 0, this is going to tell me that it is a sine function. So I have y equals some sort of an a value times sine of some sort of a b value times x. So once again, to find the amplitude, we look at the height of our wave, which is 5. So our amplitude is going to be 5. For our b value, we can look at our formula again. In this case, we're working with degrees, so we want to look at 360 degrees divided by our b value is going to be the length of one period. We can look here, our period starts at 0, and the first period ends at 180 degrees. So we can use our formula 360 divided by b value, which we're trying to solve for, equals 180 degrees, since that's the length of one period. And just like before, we can put 180 over 1 and cross multiply to get 360 equals 180b. To get b by itself, we're going to divide both sides by 180. This will leave us with 2 equals b. And we can throw that into our equation. We can also look at this. We can see we have one wave and then a second wave within 360 degrees, and that's exactly what our b value tells us. It's how many periods there are in 360 degrees. So we can use the formula, but if it's an easy value, we can also look at the graph and just count the number of periods within 360 degrees. All right, that is it for all of our examples. Thank you for watching.